I'm the supervisor of software engineering. I'm the supervisor of software engineering for the medical visualization team at Arthrex. Arthrex has a lot of efforts, or has multiple efforts, in the field of AI and machine learning. I do not know all of the efforts that they have. I only know the ones in my department, so I'm gonna talk specifically about one of the things in the ways we use machine learning and medical visualization. That's why the title of this presentation is Real-Time Anatomical Motions for Medical Visualization. As part of the medical visualization team, one of the most important things for Arthrex is really showing all of the products that the company makes on an anatomically accurate model, and showing motions and different poses for that model, just like a person would in real life pose and like make different motions when they have products on their body, that because of surgery or a procedure they had to do, right? So next slide, please. Oh, where's the, right here. There we go. There we go. Yeah, so a little bit more about me. My background is in real-time graphics. I started by creating this firefighter training simulation at FIU. That was successful. A lot of firefighters, over 100 firefighters trained, and they're still training today. More firefighters. I left the FIU. I graduated, but they're still training people using this firefighter training simulation. I then joined Arthrex, and there I was one of the main developers in their first AR application for planning a procedure for the OR. I worked on that for a significant amount of my time. And at the same time, I was working on other solutions, such as virtual visualizations of ORs, planning, operating rooms. And I also worked on this application, which right here, which we're going to talk about this one today mostly. So Arthroman is the name of this application, is a medical visualization. Where am I supposed to point? To the computer. Okay. So Arthroman is the solution we create, the Arthrex created for showcasing all of their products. It's a full anatomical model, as you can see. It has all the bones and the muscles, and it has different implants in the body. It might be hard to see from here, but there's all the different products that Arthrex made in the model. And this is an interactive application. You can come up to a podium, zoom into the model, look at it from different perspectives, see all the implants, see training videos on how they're used and what problems they solve, or you can just see a general introduction to the product. The aim is for both surgeons as well as regular people to really understand the procedure that they're about to get done on their body, right? Slide. So this is one of the installations of Arthroman. It's just a kiosk application. It was deployed to the Orlando Health Hospital, and it's there. So patients can come in and interact with this before they're going to get a procedure, and they can see all of the products, all the offerings. And there is designed in such a way that you can just go by section of the body. Is what people understand. So if you have a problem in your shoulder, you're going to go to the shoulder, you're going to see all the products and procedures and techniques that Arthrex has worked on throughout the years, with like accurate medical information. It's pretty much a collection of everything that Arthrex has for you in terms of resources, as well as animations in the form of video that you can play through and understand the process better. So this application has been really important to the company. It's really the way that people get introduced into a lot of the products when they're not already from that background, or when they're not familiar with Arthrex, because it packs everything into one application. So it's really important to the company to showcase this model. So how does this tie to AI, right? That's the big question. Yeah, and this is mainly for patient and staff education. Okay. So one of the main elements of the application is this product view over here. You can see you can see the TKA. This is one of the products that Arthrex creates for total knee arthroplasty. And this is a video that we show. So this product, when somebody puts this implant on, your knee would never be just static, right? Your knee would move using the product. And people want to know what that's going to look like. Our existing solution, the previous solution we had, only shows you static poses. And this is fine because it helps illustrate the model, but it's not really where we want to stop at. So my team hired to work on this. We hired multiple engineers and people who work on this. And the next major milestone or the next big goal that my team has is to make this posable and to have different motions. So to talk a little bit more about the software, there's products that will be used for motion, therefore they should be shown in motion. There's anatomical poses. They're individually designed and modeled. So that means an artist has to make every single one of the poses if they wanted to do different poses, or they would have to create a full animation for it. Now, Arthrex has hundreds of products. So it would be very difficult every time a new product is released, every time a new product is updated, to have to create a new model that shows all the poses, all the possibilities from the human range of motion of this product. But that's something we want to do. We want to show people from everything that you will experience when you put this on visually. So how do we do that? So like I said, large range of motions, large library of products. Those are some of the problems that we're facing. All right, another problem that we're facing is that artists have traditional tools that they use for posing 3D characters and 3D bones and muscles. But the problem with those traditional tools, these are the same tools that you see in video games and animations and things like that, is that their deformations are not accurate. So you can see this deformation here. The bone is bending, and then the hand here is bending. You can see different bends. You can see here the pectoral is stretching, and in here you can see the placement around the bones doesn't really matter. And all of these things, or artists do an amazing job of doing that correctly, but they have to work on each one of them for every pose, right? So for this pose, they would have to fix it. For this pose, they would have to fix it as well. It's a ton of work. When you start thinking about it, it requires a massive team to be able to create just a simple model that has all the different options. On top of that, put in the products, right? How the products look and how they affect the anatomy, because it's no longer, for example, the bone structure is no longer the same if they made a cut on the bone. So it becomes a really complicated task to solve, even though it's such a simple, the design it's so simple. It's just, we just need the model, we just need the body, we need to be able to see the muscles, the bones, the skin, and just see the product in there, right? So this is some of the problems that we have. And so what are some of the solutions that are in the industry? Well, today there's a series of solutions that are in traditional 3D software. One of the solutions is Blender. It's a big 3D software. It's free and open source. And they have this tissue system. And it's amazing. It's beautiful. People, artists who've worked on this, it really helps them in their process. It creates a full muscle simulation, and it has dynamics. So when you do the range of motion, it deforms the muscles properly. It deforms. It stays attached to the bones. It really works really amazingly. Right, so these are some of the solutions. Houdini is another one of the solutions that has that, and then there's also Ziva, which is another full body anatomy solution. The problem with all of these is that none of them are real-time solution except for Ziva and this new one that was just recently announced by the developers on the Unreal Engine, which is MetaHumans and machine learning. This is where the machine learning part comes in. So we have a problem that we need to generate all this motion data for our anatomy, but it would be very difficult to do it with just putting artists to it. So that's where we want to use techniques like using machine learning, AI to generate these motions and generate accurate motions instead of having to model every single frame or every single movement in the full range of motion that a human has, right? So we have these solutions that we saw before that are on these packages, but they have some problems, and that's why we need this real-time solution. So let's look at the problems that they have. Okay, so some of the limitations that the other ones have for real-time is they're limited to a rendering software. We need to create an interactive application, so we can't, if we're going to distribute this, like the Orlando example you saw, we can't have this application opened up there for people to, like something like Blender, for people to manipulate in Blender. We need to create an independent application, right? That's one of the things. Second is that those applications are really meant for the video industry, is for when you're making movies. So you create the model and then you render it out and you generate a video, right? But we want an application that's real time, that people can interact, they can zoom in, they could look around the model, they can try different poses. There's no way we would be able to achieve that by rendering this content ahead of time. So we need a way to do it in real time. Okay, then the other problem is that if we were to take something like what Blender or Houdini or any of those software do and do it in real time, we would need these supercomputers to run this simulation effectively. We can't deploy a supercomputer to an installation in Orlando Health. It doesn't make sense, too expensive, right? So there's a lot of reasons why the triangle and polygon count is not the way to go. And another one is deformations and all these physics interactions that happen when you calculate where a muscle should be placed. They're heavy on the physics calculation, heavy on deformations. Every deformation needs to be calculated per every single one of the triangles and the vertices that are in that 3D geometry. So it gets really heavy on the CPU, or if we put it in the GPU, you'll still have the same problem. You need a farm of GPUs to be able to run this. And so in general, it's just really slow to simulate if we wanted to simulate this in real time. And even when you're working in the movies industry, a lot of the times when they're rendering these solutions, they have to make tweaks on the fly and then re-render. We can't do that. It has to look good the whole time. All right, and then the last thing is you would obviously get low frame rate lag on your application if it doesn't run well. Okay, so this is one of the solutions. Ziva Real Time provides these physics-based deformations. You can see this is a representation of the bicep muscle. And you can see the deformation happening almost in real time. Now, these solutions, what Ziva provides, it provides a machine learning model that can train using this information that they generate on their software, the Ziva VFX software. That software creates the deformations that are not in real time, and then it gets taken into the Ziva RT trainer, the deformation that's not in real time, plus the one that would be shown in real time. And that generates a model that is trained, a machine learning model that is trained to take the whole range of motion and generate the appropriate deformation based on where the bone is, right? So this is one of the solutions. It's an amazing solution. This is the other alternative to the one that I'm going to focus on today, but I wanted to mention it because it's the same thing and it's really powerful. And I'll explain a little more about how it works. But these images are a perfect example, so I wanted to show it. You can see here, and this one doesn't really have a deformation on the bone, but you can see it on the muscle here. But you can see it here on the bicep. You see the clear deformation that matches what the real bicep looks like. These are all. This final result is generated using machine learning. It's a model that trains on what the real anatomy deformations are generated pre-render in power-intensive software, and applies them. The model that gets generated gets applied to a real-time model that we can use in a real-time application, like on your phone or on your computer. It's just something you can run anywhere. And this, by the way, this has full source code available. This is a paid solution. So that's why I wouldn't recommend this one. And so the next solution comes with the Unreal Engine, and it's called the Machine Learning Deformers. So they announced this at GDC 2023 as a plugin that is in preview, and it's still in preview, but it's really transformative. So you can see in here how an asset is constructed using this method. Okay, so they use a traditional software called Houdini. It's just a software for generating physically accurate anatomic geometry and deformation. And then they generate a bunch of data from that, the physically accurate ones that you really need to run on a heavy machine. So think of a computer with multiple GPUs, with a high-end CPU, right? You have this running for a period of time. Maybe you leave it running overnight for a couple of days. And this is just generating frames, individual frames. All right, and there's different options. They have an option for clothes. We're just focused, our team is mainly focused on the muscle and flesh, right? So they generate that simulated, that data, and then we use that data to train a machine learning model, which in this case is their neural morph model, which is a local model you can run in your machine. And that generates the outputs, which you'll see in a second, is the anatomy on a character. Okay, so I want to talk about the process. So the process is to create these is very simple. It's you create an anatomical 3D model. You can create it using MRI data, an anatomical modeler. Arthrex has modelers that are dedicated to this that create the full anatomic model. And then the next thing is to create the training data. And that's what you're going to use your anatomical model for. That gives you the ground base to create your training data that you would then apply to your model that's ready for real time. So the traditional model that you would see on any 3D application, right? And this machine learning model training process, once you have the data, so the next thing you do is you train your model. That is, the Unreal uses PyTorch to do this. So if anybody's familiar with PyTorch, it's a library that is used very often for machine learning and modifying models, interacting with models. They also have a C++ solution as well. And once you're done doing the training, which you just run this on a computer, that it could be on the cloud, wherever you're running it, you can run it locally. It supports running it locally on your machine, but it will take some time. It will take maybe a day, or it depends on the amount of data you have. For the type of data that we have, it will take us a very long time to train, but it's a one-time process. You don't have to do it again, right? Unless you want to modify the anatomy in the future, and that's one of the challenges coming up. But and then the last part of this is that after you run your model, it will generate this ML deformer asset, and that asset is used for generating for the real-time applications, for a runtime interference that happens when you are actually interacting with the application. So as you're going and moving your model, you're seeing the range of motion, and real time is generating the right pose for that range of motion. Okay, and what it uses in the background is Unreal has a neural network model, and it uses the open neural network exchange format to generate that model, and it can be modified. Unreal has an entire neural network solution that's very powerful, and uses the CPU, the GPU, and it could really give you access to frames in an application. So if you have a real-time application, it maybe has 60 frames running every second. It can access every single one of those frames and run inference before a frame is rendered, before a frame is shown on your computer, or even after. It can run that logic and apply it to the frame, which is very powerful. Okay, so going back to the process, so to detail a little more the process, you create an animation that applies to the base anatomy of the simulated anatomy. You set constraint for the joints, and you generate the setting constraint for the joints is you have to set the limits of how much the motion is, so the software knows what it's working with, because it's created to train anything, not just human anatomy. It's just to train with anything. So you have to really set the constraints for actual human anatomy, because it can't. Your elbow is not going to get past a certain rotation. You only have a limited range of motion. And then you run your machine learning model using this data that was generated for your model, your 3D model of the anatomy. Okay, and then you verify that your deformation in the machine learning model you create is correct, and you use that data. You can run it again if you need to modify something, and then you can use that data to apply it to your final anatomy. Okay. So these are the two options of models that they have. The neuromorph model is one set of training data. It uses random instruction, many small networks. This one uses a fully connected network. Now, I'm not, in my team, we're software engineers. We're trying to make the application. I'm not as familiar in depth with the machine learning process and that part of it. I just wanted to cover the application that we have of this particular machine learning model. This API can't be accessed through a Python API, and there's also C++ source code for it, if anybody's interested. Okay, and the process looks very simple. They have this application. This could be done through Python, but there's also a visual application. Here you have the different parts of the body. So these would be the joints, and you set your range of motion. So in this case, negative 90 degrees to 0, or negative 90 to 90. So depending on the part of the body that we're talking about, you set the range of motion, and then you generate your training data based on that. So it will take your model that you created in software that pre-renders the model, and it would apply it. It would generate some data that you can then use in your training model. Okay, so here's an example. Here, this helps you visualize it really well. So this is what's generated. This is a single frame that's generated in a software like Houdini or Maya or any of the traditional 3D software. This cannot be shown in real time because it's just one frame, that whole model, right? So you would have to show multiple of that model for it to work every frame. And this is a character that's actually real time. So this is your training base. And the green is the differences between this model and the character when it has all those benditures that you have before it was trained. This is before it's trained, right? So this is what you see before it's trained. Okay, so when you run this, you got to make sure you verify. This is the process of verifying that your data is correct. What is the training model going to do? Okay, and then you can see here some of the results. So you can see this deformation here doesn't look good. I mean, it's hard to see. I wish I could zoom in more, but you can see the deformation on the ML deform right here is correct. This is not how human anatomy works. Right? Same thing here. This is very pointy, but you can see here, you can clearly see the muscle. You can see that. You see it? Yeah, because it's very far away. But yeah, you can see the results here through the skin. It's very powerful what it does. It's really amazing that what this tool does, and we really want to be able to apply this to our Arthroman model. And here's the results with muscle. The same thing here. You can see the bicep deformation here is really well done. You can see it here in this model. Everything's deformed and covered. This is an animated model. I can show a video as well if anybody's interested. I just put these static slides, but this is better seen obviously when you have the motion. But you can see these deformations here on the biceps. You typically wouldn't see those on a character in real time. This is all running in real time. And so the results are just fantastic. I mean, it's night and day, and these are things that we couldn't do before on real-time applications. And here's our Arthroman. You can see the muscle deformations. some of the challenges that we faced is that batch training of muscles. We want to be able to do this not just for the whole body, but we want to do it for each individual muscle. So it's very difficult because there's no solution yet for training for every single muscle. The neural network takes one base mesh, which is your base data, and then it uses this modified mesh as your training data, but it needs thousands of frames of that modified mesh, right? But if we wanted to apply this to every single muscle, now we have to do the same process, run the model for every single muscle. So that's something that we still have to overcome. And then the other problem is dealing with muscle updates. So now you've trained the model, it looks great. You have an amazing product, your anatomy looks fantastic when it's moving, but you want to modify a specific muscle that, I don't know, there's maybe a new process or a new product came in and you have to modify the bone, and the muscle is going to be different on the bone, the way it lands, or there's going to be a different deformation because you have that product on the person installed, right? So you have to deal with those updates, and they don't really have a solution right now using the training model that we can just modify the model slightly to deal with those updates. We have to retrain all over again. Right. And another one of the challenges is that we need faster way of generating the data. The data still takes a long time to generate, takes days. We have to, depending on the amount of data that you have to leave this thing running for a very long time. I mean, one way is to throw more GPU, more CPU power, but they really need a faster way to generate the training data. So whenever we iterate, we don't have to run through this long process again. Okay. And that's it. That was my presentation. Anybody has any questions? Yeah.
Yeah. So you kind of hit on it right at the end, but normally, right, to have good machine learning, you want good massive data sets. So are you saying like every single static image that gets put into the learning algorithm is like done by hand, and is it like verified? Is there like, how does that work?
Yeah, so the data is generated using those the previous software that I showed, Houdini. So they generate the data that we need. The problem is, the challenge is that, well, if we have to when we have to modify it, that's when the biggest challenge comes in, because then you have to add additional data, but you can't use an existing model, or at least not with this solution. Can't use an existing model and train it with additional data and hope that it will improve. The problem is that you need to retrain the model completely. So I'm hoping that in the future they'll have a way to tweak the model so that it can improve with additional data. But we generate the data using the simulations that we get in the same type of software that is used to render for movies and things like that, things that can't be done in real time. The solution here really is the ability to take this information and run it in real time, in a real-time application, run it on a browser, on a laptop, on a phone, right? Because we're using these systems. It infers the solution.
So what is the data that you're actually using? Like she had mentioned images, but I'm guessing
they're 3D models.
It's all 3D models?
Yeah, it's all 3D models. They're frames, but they're frames over 3D model. So it's pretty insane, the size of this. It's a frame because it's just one frame of like a still in a video. So if you're doing a motion, it's just this one still. But this still is not a picture. It's a 3D model of the still. So it's a full mesh.
You mentioned the MRI stuff. Is that being incorporated?
Yeah, so the MRI, it's really a way you can pick different ways to generate your original model. There's sometimes in medical visualization, we try to use mostly artist model, because the problem is that when you use MRI data, they're specific to one patient. And the problem with that is that not everybody's the same, right? So you want to have more of a generalized model, and that's typically where artists come in and they really do a better job of creating a human that's general versus a human that's very specific from the MRI data, but it could be done with MRI data as well. Yeah. Yeah. Yeah, I mean, it would work if it was for one person. If you wanted to do it really well for one person, then MRI data would be amazing. But the problem is when you want to generalize it. Now you need anatomy that's general unless you had MRI data for like a vast amount of people. Yeah. Yeah.
How many?
Yeah, so the one that we had there, I think it, let me see if I go back. I think that one shows it. It's let's see. Let's show it. Oh, okay. Nope. Yeah, well, I cut it off of there, but it could be, I mean, it really depends on the complexity of the movement. For example, but a very simple movement, it could be up to 5,000 frames just for a bicep curl, right? Yeah, it's a lot of data. And those are not, again, those are not images. Those are like the full motion. It's a 3D capture of the full motion. So it's like the whole body. Or if we're just training the bicep, we would.
All 5,000 artists.
Yeah, that's where the software comes in. The artist has to tweak it, but the software helps a lot because the software generates physically accurate motions and deformations on the anatomy. But there's always the medical, Arthrex works with medical education, and medical education comes in and they verify that those deformations are correct on almost different poses. They don't go frame by frame, but they go at different poses that are the general poses. Yeah. Yeah. Yeah, but that's where the model comes in. We don't have to do we don't have to generate every single frame. The model can use different frames and use the data, any data that's generated in between those frames, the model can use, even if we didn't have to manually adjust that. You just have to make sure that it's proper and it's good at certain points. So the model does an amazing job of handling that problem. Yeah. Any other questions? All right, well,